Swayam Prabha. Digital India. Educated India.
Previous lecture we have seen some simple rotor model in which we considered the flexibility of the bearing, and especially when we considered the hydrodynamic bearing model, there is 8 linearized coefficient of the stiffness and damping, and we showed that those coefficients we can able to calculate at equilibrium positions, and that equilibrium position changes with speed. So, these coefficients in actual practice they will vary with speed. So, whatever the analysis we did earlier that can consider the speed dependency of such stiffness and damping coefficients of the bearings. Today we will study effect of gyroscopic couple on the natural frequency or the critical speed of the system. This gyroscopic effect generally occurs when the disc is spinning at high speed and it is wobbling. That means when simultaneously tilting of the disc is taking place during the whirling motion. And because of this particular gyroscopic effect, we will see this, that even the natural frequency, the whirled natural frequency will now no longer will be equal to the spin speed. So, if we are considering a perfectly balanced rotor and if we are operating at certain speed, the whirled frequency may not be equal to the spin speed. And so, for this particular case, we will see that as we are changing the speed, the gyroscopic moment changes, and that changes the whirl frequency. So, the whirl frequency basically now it will depend upon the speed of the rotor itself. Two things we will observe, especially regarding the natural frequency, that in this particular case when gyroscopic effect is there, the splitting of the natural frequency we will observe, and this particular phenomena we will see in subsequent lecture. Today we will concentrate on synchronous whirl condition, in which we will try to calculate the critical speed rather than obtaining the whirl frequency. So, with this particular module of the gyroscopic couple, now the definition of the whirl frequency, critical speed, they will be quite distinct. And we will observe that we will be having phenomena of forward whirl and backward whirl also because of the splitting of the natural frequency, and corresponding we will be having critical speeds also, which will be having forward whirl and backward whirl, in which case the spin direction or the spin sense of rotation and the whirl sense of rotation may be same or different. So, for this particular case, this is the overview of the lecture, in which we will be doing the analysis of a simple cantilever rotor with a thin disc at the end. We will not consider the mass of the shaft, only the elasticity of the shaft will be considered, and disc will be considering as a rigid, is having no warping of the disc in this particular analysis. In this we will see that the gyroscopic couple effect onto the critical speed. Basically, we will be calculating what is the critical speed because of this gyroscopic couple, and some concepts which we will be covering in this lecture is the gyroscopic effect, disc effect or the diametral mass moment of inertia, how it changes the critical speed of the a rotor system. So now with some simple example, let us see when this gyroscopic couple will be predominant, and let us take a simply supported case in which this is the bearing axis and we have rigid bearings, that is simply supported condition, and this is the shaft elastic line. Let us say disc is at the center of the midspan of the shaft. So during whirling, we will observe that disc would not tilt. It is spinning about its own axis with omega, but disc tilting will not take place because is there at the midspan, and at midspan the shaft slope is 0. So during whirling of this, there will not be any tilting of the disc would take place. So once this disc is not tilting about its diameter, there will not be any gyroscopic couple effect onto this particular system. But if the same system is there with disc at offset position, so let us say here. So in this particular case, because the disc at any particular position should always be perpendicular to the shaft elastic line, so we will find that the disc will tilting about its one of the diameter in this particular plane. So not only we are having spinning of the shaft, but the disc itself is having some kind of precession frequency, and that is the whirling frequency of the disc. So this wobbling motion of the disc along with the spinning of the shaft would give the gyroscopic couple. So we expect this gyroscopic couple effect will be present in this particular model. Another case, if we consider, let us say a cantilever shaft, and this shaft is massless, only elasticity is there, and let us say disc is in the form of a point mass m, and if this is spinning at certain frequency during whirling, we expect this will occupy this position. So this is one of the case. If this particular cantilever beam is having a large thin disc of the same mass, but having diametral mass moment of inertia of the disc, in this particular, because this point mass, diametral mass moment of inertia will be nearly 0. When this is spinning, we will find that during whirling, this disc would be tilting about its diameter. So in this particular case, we expect a gyroscope. So you can able to see there will be precession frequency of the disc would be there. So if we consider this particular model of the rotor, and in this, in which the mass at the free end are same, but only difference is here is point mass, here it is disc. So we expect the critical speed of this system and this system should not be same, and especially when this particular speed is high, we will find that the gyroscopic couple will make the critical speed of this system and this system are different. So with this example is very clear that when the gyroscopic couple will be present in the system and when it will not be present. So when point mass is there in a cantilever beam, we cannot expect a a gyroscopic couple in that, because its diametral mass moment of inertia is 0. So now we'll consider a simple cantilever beam. We will not be considering any unbalance of that in that particular disc. We are assuming that there is no unbalance in the disc, and we are operating near the critical speed of the system, so that the natural frequency or the whirl frequency is equal to the spin speed. As I mentioned, when gyroscopic couple is there, the whirl frequency and the spin speed may not be same, but in this particular case we are considering a very special case in which we are trying to find out at what whirl frequency the spin speed at what speed it is the whirl frequency is equal to the spin speed. So, that means we are trying to find out directly the critical speed of the system, and in this particular case let us try to analyze a cantilever beam with a large disc at the free end. So, if this is the disc, this shaft is spinning and disc is also spinning with the same speed, and because of this we will see that for this particular configuration, let us say when the shaft is at the bottommost position during whirling, if we try to see for this particular instant how the centrifugal force of various masses of the discs are acting. For this particular instant, we will see that the mass element which is away from the spin axis will be having large centrifugal force, because it is spinning about this. As we will come toward the spin axis, this centrifugal forces will be lesser and lesser, like this. Now, if we see the effect of this centrifugal force, what they are trying to do to the disc, they are trying to apply a couple which is acting in counterclockwise direction. So, it is trying to orient the disc to its original vertical position, because the tilt of the disc during whirling is this angle, and this particular moment is trying to oppose that tilting which is coming from the centrifugal force. So, we will see that because of this moment, effective stiffness of the shaft against the rotation is becoming higher, because this particular moment is trying to prevent the it is making this particular angular displacement lesser and lesser because of the this moment, and you can expect that when the centrifugal force is high at, if we are increasing the speed, as we are increasing the speed, this will be more and more, and we expect this moment will be more, and because of that effective stiffness of the system increases. And as we know from fundamental that the natural frequency is defined as root square k by m. So, if stiffness is increasing, mass is same. So, we expect that the natural frequency of the system should be increasing. So, we will find that in this particular case, when we are rotating the rotor at certain speed, and we are trying to find out a condition for at what speed the whirl frequency is equal to spin speed for a balanced rotor, the effective stiffness is increasing, and because of that the natural frequency is also increasing. So, this particular phenomena which I have illustrated through the centrifugal force concept we will see in more detail through the concept of the quasi-static analysis, in which we will be finding out what is the effective the force and moment this particular centrifugal force are applying at the free end of the shaft, and from there we will try to get the frequency equation to calculate the critical speed of the system. Now we will analyze how the whirl frequency of the system increases with the spin speed of the shaft because of the centrifugal force. Let us, for that particular case, we will take the same example, and now we will see this particular disc from side, how this particular system is giving us the okay. So, let us say this is bearing axis B 2, and this particular axis, bearing axis, we are representing as a Z, or this angle is, or let us say this direction is Y. So, this angle will represent as phi x. This is the static deflection, let us say delta of the center of the shaft or the disc. So, here let us say the intersection of this axis to the disc is I am writing as B. This is the shaft center which is coming from here, and this B to C is distance, that is translatory displacement of the shaft from its equilibrium position of the bearing axis. Now, if we consider a small mass, let us say this is at radius r1 from the bearing axis. So, if we see the motion of this particular disc, and as I told, we are looking into the condition of synchronous whirl. So, let us see this particular motion, what it represents. So, in the synchronous whirl condition, the spin speed, that is the spinning of the disc, and the whirling frequency, this is the whirling frequency, let us say this is the cantilever beam. So, this whirling frequency and the spin should be same. Now, when we are considering this synchronous whirl condition, so what will happen for this particular case, the shaft will bend, and once it is bent, it will be rotating about bearing axis in the rigid body mode without the bending and without bending of the shaft. So, bending of the shaft, if we see the fibers in this particular shaft which is in tension, will be always be in tension during the whirling, and which is compression will always be in compression during whirling for the synchronous whirl condition. So, it will be as a rigid body, it will be rotating about the bearing axis. So, that is a synchronous whirl condition, and in this particular case, if we see that each and every particle onto the shaft will be making a, if shaft is symmetric, a circular path. It will be making a circular path about the bearing axis. In also on the disc, if we take any element of the mass, that also will be making a circular path. Maybe the radius of the circular path will be different for each of them. So, in this particular figure, the R1 which I have shown here. So, this particular disc during the synchronous whirl will be making a circle with the R1 as a radius and bearing axis as the center. So, it will be making a circular motion. So, we can expect that because of this, the centrifugal force which will be acting on this mass, let us say this mass is small dm. So, this will be along the direction of the R1 only. So, let us say this is centrifugal force m dm omega square R1. This is acting along the direction of R1. Now, this particular motion of the whirling, again let us see this particular whirling motion. So, this whirling motion which I told for synchronous whirl is taking as a rigid body about the bearing axis. So, and it is spinning also, both are taking place. Because of that synchronous whirl is taking place. If we consider this motion in two parts, one is pure spinning at omega rpm or radians per second, and then without rotation, only whirling. So, basically in actual case both spinning and whirling take place simultaneously, but now I am considering spinning separately and whirling separately. So, in this particular case the disc is not spinning, only it is whirling. So, in this particular case we will see that the two motion which was spinning and whirling simultaneously, which was taking place, we have split in two parts. So, when we are considering the spinning, so we can able to see that this particular mass for that particular rotation, when we are considering pure spinning, it is spinning about the center of the shaft. So, that means we can able to take the centrifugal force because of this as, if let us say radius of the disc is r, this will be dm omega square r. And another case is this one, the pure whirling. In that particular case we expect this particular mass at this particular configuration will be, again I can able to show here this, when pure whirling is taking place. So, when disc is coming from, let us say, top to bottom, so when it has reached at the bottom, the direction of the centrifugal force of that mass due to this whirling will be toward the downward direction. It is coming. So, at this position the centrifugal force will be downward direction, that means vertically downward. So, this component is that particular direction, and this will be dm omega square delta, because now when the disc has reached at the bottom, each and every particle of the shaft is having delta displacement. So, we will be having this particular force, centrifugal force. So, you can able to see that the total displacement which is total centrifugal force, which is dm omega square r1, is summation of these two components due to pure spinning and pure whirling. This particular forces which now we have got, now we will take the forces component of this in two planes, and we will try to find out, because of these forces, what is the resultant force and moment which is actually coming onto the rotor system, for which I am drawing let us say in one of the plane, let us say this is z axis, bearing axis, and y vertical axis, and disc is this one. So, this is the disc only I am showing it, and let us say there is a particle here having mass dm, let us say that point is P, and this is the shaft which is attached to the disc. This is the shaft. Now, this is the center of the disc, C here. Tilt is about x axis, so phi x. Now, this is the case for pure whirling case. Pure whirling motion, there is no spinning. So, if you see from side of this view of the disc, let us say this is y axis and this is x axis, particle P is here, is at radius r. And this is the center of the disk. Now, if we see this particular force which is acting downward direction. So, for this particular configuration, not only this mass, each and every mass will be having same inertia force, because each and every particle of the disk is having delta displacement. So, this particular mass dm which is there at P will be having a force m omega square or dm omega square delta. Each and every particle will be having same force. This particular force on this plane is in this direction. So, this is dm omega square delta. If we consider another point diametrically opposite to this here P prime, this will also be having same direction force, same magnitude, because the particle is dm. Here if P prime, if we consider, it will be having downward direction dm omega square delta. Now, you can able to see that if we consider all the masses in the system, they will add up and they are not cancelling each other. Basically, all the forces are downward. So, if we add all such forces, this is for the elemental mass. If we add for all such masses of the system, we will get a net force, and the direction of that force will be in the y direction. So, this is the net force which will be acting due to the pure whirling case. Pure whirling motion. Regarding in this particular case, they are adding up to give the force in this. What about the moment? You can able to see this particular particle and this particle will produce about the center moment, which will cancel each other because they are opposite to each other. So, there will not be any net moment due to this here also. If we try to take moment about this point, these two will cancel each other. So, the net moment due to the whirling motion will be 0. So, moment will not be there due to the whirling motion, only this particular total mass of the disk into omega square delta force will be acting on this particular disk. Now, let us see the pure rolling motion, pure spinning motion. Now we will consider the pure pure spinning motion of the disk. So, in this particular case, I am again drawing the free body diagram of the disk in, let us say, z y plane. Z is the bearing axis, disk is here, shaft is this one. Now, if we take the diagram in other plane, we will see the disk like this. This is the center of the disk C. These are the y axis and x axis. P particle is, let us say, here, and radius of that is r. Let us say this inclination with respect to x is theta. Here, because of the pure spinning, we have centrifugal force omega square r dm, which is acting radially outward. This particular force we can able to take component in two directions. This particular, from here we can able to relate, let us say, this distance is y and this distance position of the from the position of the mass is x. So, we know that x is equal to r cos theta and y is equal to r sin theta. So, the component which is there in the horizontal direction here will be having value omega square r dm cos theta. This will be acting in the x direction, and if we combine the r and cos theta, this can be written as omega x dm. Similarly, this is in the x direction. Similarly, in the y direction, the force component will give us omega square r dm sin theta, that will give us omega square y dm, because r and sin theta is y. Now, this particular force in this plane, if we want to see, the y component is acting in the direction of y, x component is acting in the direction of x axis. So, if a particle is here, the force, one force is there in this direction, the magnitude is omega square y dm. Other force, the x direction is, that is perpendicular to the screen, into the screen, because according to the right hand rule, it will be inside the screen, x will be inside the screen. So, this particular force component which is in x direction will be in the plane of the disc. So, we cannot able to see that particular force here, that will be on the plane of the disc, but the y component is along the y direction. So, we can able to see that this particular component is not on the plane of the disc. Now, this particular distance, we can able to see that this is y distance, this angle is phi x. So, this distance will be y into phi x, because this is y and the angle is phi x. So, this distance will be phi x. So, the component of this particular force will be making y phi x distance from the y axis. Now, if we see this particular particle x component, which is this direction, if we take a particle here opposite here, so this particular force and this particular mass force will balance each other, because they are in the same plane. If we consider another point, let us say below, this particular force in the y direction and this particular force, if we consider here p prime, let us say, which is below, this will act, because it is spinning, so it will act in this direction. The magnitude of this will be same as the upper one. So, you can able to see that they will make a couple. They will balance each other, but they will make a couple, and the magnitude of the couple we can able to find out will be, so let us say for single mass dm, the couple about the bearings, the shaft center will be, that is in the yz plane, omega square y dm is the force, and moment arm is y phi x. This is the moment arm, this one. So, this is a couple due to a mass dm. If we sum such moments, we can able to get the total moment due to the various forces, and that will be giving us this, and because omega is constant, it will come out. This is also independent of this integration. So, we will be having y square dm, and we know y square dm is nothing but diametral mass moment of inertia of the shaft, of the disc about its diameter. because in this particular case, so in this particular case, when we are considering the pure spinning, I will speak on here. So for the case of pure spinning, we found that the x component forces are cancelling each other, whereas the forces in the y direction, they are giving a pure moment, and that moment is the gyroscopic couple moment. And in the previous case, the pure whirling case, we saw that the net force, centrifugal force we were getting. So effectively, because of the pure spinning and pure whirling, we got one force and one moment, and now we will be using this to get the frequency equation. So from the previous analysis of the pure whirling and pure spinning, if we remove the disc onto the shaft, we will be having inertia force and a moment. And direction of moment in the previous slide we can able to see is this particular force is producing a counterclockwise in YZ plane. So that particular direction we have retained here. Now effectively now our problem is to we have converted the dynamic forces into a static force. So that means basically we have converted a dynamic system to a quasi-static system, and now we will be obtaining what is the deflection and angle because of this particular forces. And from strength of material deflection theory, we have such relations, like for displacement, the linear displacement is given as because of the force and because of moment. So this is the linear displacement, and force and moment, if we are applying, we will get this relation. Similarly, for angular displacement, we have relation Fy L square 2 EI, then due to moment, because we are dealing with the linear system. So because of this moment and force, displacements can be added up to get these relations. So this is coming from the deflection theory of the strength of material. So any strength of material book can be referred for such relations. Now we need to substitute the centrifugal force and gyroscopic moment in this expression. So we can able to substitute like this: gyroscopic moment and similarly in the deflection rotational displacement. Now we will see that these two equations, this equation 1 and 2, basically each and every term, they contain either linear displacement or translatory displacement or angular displacement. Here also delta is there, here also phi x is there. So all terms containing, so basically they are homogeneous equation. We can able to rearrange these equations like this: m omega square L cube by EI minus 1 delta. So I have taken this in one side and I have taken the delta common, plus minus ID omega square L square by 2 EI phi x is equal to 0. So this I have obtained from equation 1. Similarly, from equation 2, we can able to get delta plus d omega square L by EI minus plus 1 phi x is equal to 0. So I have expressed this, let us say this is equation 3 and 4. So equation 3 and 4 now we can able to put in a matrix form. So we can able to write this as y phi x, and because this is homogeneous equation, right hand side is 0. So here we have m omega square L cube by 3 EI minus 1 first term, then minus ID omega square L square by 2 EI, and here minus omega square L square by 2 EI, and here ID omega square L by EI plus 1. Now this is homogeneous equation. One solution is when both displacements are 0. So that is the case when we are not considering the motion at all. So for non-trivial solution, for non-zero displacement, the determinant of this matrix should be 0, and if we put the determinant of this matrix 0, we will get a polynomial in terms of the omega, which is the critical speed of the system, because we started with the whirl frequency is equal to omega. So we were looking for the critical speed of the system directly. So we will get a polynomial in terms of omega. Basically it is a quadratic in omega square. So this equation will be, after rearrangement of this equation, this is the square term, then a constant term, equal to 0. So this is a polynomial, and you can close the bracket. We can able to solve this for omega square. The polynomial which we have got is basically a frequency equation, and we could able to solve in terms of omega square. But in this particular expression, several variables are there. Now we will try to reduce the variables so that we can able to do better interpretation of this particular equation. So I am defining two terms, non-dimensional terms. So first is the critical speed effect. Critical speed function. So that is a non-dimensional term defined as spin speed m L cube by EI, and another is a mass effect, disk mass effect. This is a mu that I am defining as diametral mass moment of inertia divided by m L square. So, these two are the non-dimensional terms. We can able to use this to rearrange this polynomial, and if we do it, we will get a much simpler expression in terms of the non-dimensional parameter we defined. So, this is much simpler, and in this you can able to see there is a only single disk parameter is there, others are included in the non-dimensional terms. Now, the solution of this we can able to get, because this can be solved in closed form. So, the solution will be of this form. We are getting two roots like this, but if we see carefully this expression within the bracket term, within the square root term, this particular disk effect is positive. So, this will be positive, this is a positive. So, we can able to see that this term which is within square root is always greater than this one. Now, if we take the negative sign, we will get this particular the critical speed as imaginary quantity. So, that is not a feasible one. So, we can neglect the negative one and we will consider only the positive sign here. And with this, if we plot the omega critical versus mu at mu is equal to 0, let us say. So, for mu is equal to 0, we cannot able to solve from here. We need to go here, we need to multiply each quantity by mu. So, we can able to see that this term will vanish, this term will give us, for mu is equal to 0, from the frequency equation we will get 4 omega bar critical square, and we will get minus 12 is equal to 0. So, omega critical square is equal to 3. So, here for 0 mu we are getting value of this as 3. Another case, when mu is infinity, tends to infinity, we can able to see that these terms will vanish and these terms will vanish for infinity, and if we simplify we will get this as equal to 12. So, that is here, let us say this is 12. So, mu is equal to infinity means a very large disk, or the disk with large mass moment of inertia, because diametral mass moment of inertia, because mu is defined as ID by ml square. So, if this is large, then this should be very large. So, for that particular case, so if we plot this particular equation, we will get a curve like this. Asymptotically, it will this critical speed will be equal to infinity when it will be equal to 12 when this particular frequency ratio, this disk effect is very large. So, you can able to see, if we say this one, when mu is 0, what is this case? Mu is 0 means, if you see here, ID is 0. So, there is no mass moment of inertia of the disk, that means that particular disk is a point mass. So, this is representing as a point mass disk. This case, when is having infinite diametral mass moment of inertia, so inertia will be so high that disk will not tilt in that particular case, and this is the general case of critical speed in which it is varying with the disk effect. So, if disk effect is more and more, if diametral mass moment of inertia is more and more, we will be seeing the critical speed is increasing continuously, but it is having some maximum value is equal to, that is equal to 12. The critical speed square is 12. There is a non-dimensional parameter. Today's lecture we have seen that how a critical speed for synchronous whirl condition of a cantilever beam we have obtained. In this particular case, we have considered a very special case in which not only the motion is the synchronous whirl, that is the spin speed and the whirl frequencies are same, their direction is also same, and we have seen that as we are increasing the disk effect, we are increasing the gyroscopic moment, and because of that we are having increase in the critical speed. So, as we have seen in the beginning of the lecture, the centrifugal force tries to tilt the disk to its original position. So, it increases the stiffness of the system, and because of that the critical speed should increase. So, finally, we have seen that particular effect, as we are increasing the disk effect, the gyroscopic moment will be more and more, and will be having increase in the critical speed of the system due to the gyroscopic effect.